This is an introductory video for the 6th physical chemistry topic in AQA A-level chemistry. In this video we're going to look at the equilibrium constant Kc, how to write an expression for it, what the units are, and also how to calculate a value for it just by substitution. The next video will look at ice tables and how to calculate the equilibrium moles that you're going to need in order to complete complex Kc calculations. As you know, in a reversible reaction, the products can react together to form the reactants again, and this is signified by this reversible reaction arrow. When a reversible reaction occurs in a closed system, in other words no matter and no energy are being added in or taken away, then the reaction may reach a stage called equilibrium. At equilibrium, the forward and reverse reactions are happening at the same rate or the same speed, and this means that the concentration of the reactants and the products is no longer changing, because the forward reaction happens at the same speed as the reverse reaction, and therefore the products are made at the same speed as the reactants. Crucially, the concentrations of these two sets of chemicals is not necessarily the same as each other. In fact, it's very rarely the same as each other, and there's a whole chemical industry built around trying to make sure that there's as much product concentration as possible and as low reactant concentration as possible. We can demonstrate the exact position of the equilibrium mathematically with an expression called Kc. This is a number that we can calculate which will tell us whether the forward reaction or reverse reaction is being favoured. If the value of Kc is higher than 1, then the equilibrium lies to the right and there are lots of products being made. If the value of Kc is less than 1, then the equilibrium lies to the left and there are more reactants. Kc is the first of several different equilibrium constants that you'll meet in A-level chemistry, but they all take roughly the same format. The first thing that you need to remember is that the products are going to go on the top of this expression with the reactants underneath them. The second thing is that we're going to use powers for coefficients. So you can see here that in my chemical symbol equation I have 2 moles of B, and therefore B is squared in the expression, and likewise I have 3 moles of C and 3 is cubed. The last thing to note is that we have square brackets in this expression, and the square brackets denote concentration. Now this could be because you're dealing with a solution where you know what the concentration is, but it could also be a gas where you're given a volume and you need to calculate a concentration yourself. So based on that information, you can pause the video and write an expression for Kc for each of the following reactions. Remember, you need to be using square brackets for concentration, and you should have the products on the top of the expression and the reactants below, and use powers to represent the coefficients. So for question number 1, your expression should look something like this. We've got the products on the top, the reactants on the bottom, square brackets, and your concentration of both water and ethanoic acid are squared because there are 2 moles of them in the symbol equation. Then for the Haber process we have something that looks like this. Again, ammonia is squared and hydrogen is cubed because there are 3 moles in the symbol equation. Then the production of hydrogen iodide looks like this. Then for question number 4 you should have this, and for question number 5 you should have this. Kc doesn't have one standard set of units. You're going to need to work it out afresh for every Kc expression that you write. But remember, Kc is built up of data that's concentration data, and concentration is measured in moles per decimetre cubed. So if I wrote this out longhand, for the expression I started with, I've got 4 different sets of moles per decimetre cubed on the numerator of my fraction, and 3 different sets on the denominator. So therefore I can cross out these, I can cancel them out, and what I'm left with in this particular instance is just one example of moles per decimetre cubed. Moles per decimetre cubed are pretty standard units that you're comfortable with, so let's look at something that's a little less familiar. Here I have 1 mole of X reacting with 2 moles of Y to produce 1 mole of Z. So my expression for Kc looks a bit like this. Again, I can add in moles per decimetre cubed for each different concentration. So I'm going to have 1 on the top of the fraction and then 3 on the bottom. One of those cancels out, and therefore I'm left with units of 1 divided by moles squared decimetres to the -6. So therefore that simplifies to be moles to the -2 decimetres to the 6. Another way you can think of this is that the units for Kc will be moles per decimetre cubed to the power of the change in moles. So for instance, if I start out with A reacts to form B plus 2C, I've started out with 1 mole and I've gone to 3 moles, so that's a change of plus 2 moles. So therefore my units would be moles per decimetre cubed to the power of 2, which would be moles squared decimetres to the minus 6. If instead of that I had 2A plus B reacting to form a single mole of C, then I've gone from 3 down to 1, which is a change of minus 2 moles. So we do moles per decimetre cubed to the minus 2, and we'd have moles minus 2 to the decimetres to the 6. Now if I had 2A plus B reacting to form 2C plus D, and I had a change of 0 moles, then I'd end up with moles per decimetre cubed to the power of 0. And anything to the power of 0 is just 1. In other words, if there's no change in the number of moles, then there's no units at all for Kc. Here's an opportunity for you to pause the video and write down what you think the units are for each reaction. In question 1, the number of moles has decreased by 1. In question 2, it's decreased by 2. In question 3, it hasn't changed at all. In question 4, it's increased by 1, and in question 5, it's decreased by 2. So based on that, we can see that the units for question 1 will be moles to the minus 1 decimetres cubed. The units for question 2 will be moles to the minus 2 decimetres to the 6. Question 3 won't have any units because there's no change in the moles. Question 4 will just be your traditional moles per decimetre cubed. And question 5, like question 2, will also be moles to the minus 2 decimetres to the 6. In order to calculate a value for Kc, we need concentration, and up until now you might have only met concentration in the context of solutions. But of course concentration is just an expression of the ratio between the number of moles and the volume that they're in, where that volume is expressed in decimetres cubed. So we can also work out a concentration for gases, provided we know the size of the container that they're in. For instance, if we look at this sulfur dioxide, we've got 0.6 moles divided by a volume of 200 centimetres cubed, which of course we can convert to 0.2 decimetres cubed. That gives me a concentration of 3 moles per decimetre cubed. Pause the video and calculate the concentration of the remaining 4 gases. For the ammonia, we do 0.75 moles divided by 0.15 decimetres cubed to give us a concentration of 5. Then for the hydrogen, we need to be aware that this is in metres cubed. So there are 1,000 decimetres cubed in a metre, and therefore this is equivalent to 200 decimetres cubed. So therefore we're going to have a concentration of 0.004. Then for our nitrogen dioxide, we're going to do 0.45 divided by 0.9, and that's going to give us a concentration of 0.5. And then finally the methanol, we're going to do 0.24 divided by 0.06 decimetres cubed, and this will give us a final concentration of 4 moles per decimetre cubed. The vast majority of calculations that you complete in AS and A-level chemistry with Kc are going to require you to work out for yourself the number of moles that are present at equilibrium, and we'll look at that in the next video. But for now, I just want to practice substituting in some values. So in this question, we've been given the moles for a reversible reaction where carbon monoxide reacts with 2 moles of hydrogen to make methanol. So the first thing that we're going to need to do is to turn those moles into concentrations, because we've been given a volume here, and I've kept it nice and straightforward, and that's a volume of 0.5 decimetres cubed. So this is going to be quite easy maths as a result. So for my carbon monoxide, I've got a concentration of 0.68, and then for the hydrogen, it's going to be 0.38, and then for the methanol we have 0.1220. So now that I have those, I can write an expression for Kc. So remember, we're going to have our products on the top and these square brackets remind me that I'm using concentration, not just the moles. That's a really common, easy mistake to make when you're starting out. So I'm going to have 0.1220 for my methanol divided by 0.680 multiplied by 0.380 squared. And all of that together is going to give me a value for Kc of 1.24246, and it sort of carries on for a bit. So since the values in the question are given to 3 significant figures, I'm also going to give my answer to 3 significant figures. And the fact that I've got an answer that is larger than 1 tells me that I have more products than reactants, so the equilibrium is lying over towards the right hand side of this equilibrium. Here's another really similar question using the same reaction for you to have a go at. So pause the video and then we'll work through it afterwards. So again, I've got carbon monoxide reacting with 2 moles of hydrogen in order to produce methanol. And that means that my Kc expression is going to be exactly the same. So I need to work out the concentrations in each instance. So 0.252 divided by 9.4, because 9.40 times 10 to the 3 centimetres cubed, I know that there are 1,000 centimetres cubed in a decimetre cubed, so I'm just going to get rid of that 10 to the 3 and make this decimetres cubed. So that is going to be 0.026809. That's my carbon monoxide. And then 0.206 divided by 9.4 is going to be 0.021915, that's my hydrogen. And finally 0.273 divided by 9.4 is going to be 0.029043 for my methanol. And those are all concentrations now. So those are the values that I'm going to put into Kc. So I'm going to have 0.029, etc. Obviously I would use my full calculator display, but otherwise we'll be here all day waiting for me to write these things out. And this needs to be squared because it's squared in the expression because there are 2 moles of hydrogen in the equation, and that gives me a final answer of 2,255.711, which to 3 significant figures is 2,260. And then I also need some units for this because this question has asked me to state the units. So if again I look, I've got a change going from 3 to 1, so that's a drop of 2 moles. So my units are going to be based on moles per decimetre cubed to the -2 because it's a drop of 2, so that's going to be moles to the -2 decimetres to the 6. Thank you very much for watching, and I hope you found that a useful introduction to Kc expressions. In the next video, we'll look at how you actually go about calculating the number of moles at equilibrium. If you did find it useful, then don't forget to like and subscribe for more A-level chemistry content coming soon.